Today's session will be first some theoretical knowledge about nonlinear static analysis. So it's not an easy type of analysis, so there's a lot of things to say. I tried to make it as simple as possible for you. I will have also two tutorials for you. One will be a leaf spring to show you how to assign nonlinear material, and the second one will be a gearbox analysis. Okay, so let's begin. So the first thing you have to know is that most of the physical phenomena are nonlinear. So it's really something that it cannot be neglected. If you see this picture, all these phenomena are nonlinear. So you have three types actually of nonlinearity. One is the geometric nonlinearity on the left. So if you have excessive deformation, for example, or if your loading is changing during the analysis, there you have a geometric nonlinearity. Second type is the material nonlinearity. So basically, if you have a nonlinear stress and strain curve, or if you're using elastoplastic and hyperelastic models for rubbers, for example. The third type of nonlinearity is the changing of the contacts during the analysis. So it can, in Midas NFX, it's called general contact. So at the beginning of the analysis, the two surfaces are not in contact, and it enters in contact afterwards. So before explaining nonlinear, which is much more complex, let's just take a look back on linear analysis. So linear analysis is actually a simplification, let's say, of the model. If you look on the curve on the right, you see this portion can be assimilated as a linear curve and with a fixed coefficient k. So actually the Hooke's law, which is at the basis nonlinear, has been simplified in order to become linear. So for linear analysis, a force of 1 kilogram will make 1 millimeter deformation. A force of 10 kilogram will make 10 millimeter deformation. So as k is always constant, the force value can be obtained easily. Now let's check what is nonlinear. So the big difference between nonlinear and linear analysis is that the k coefficient is not constant anymore. So as you can see here, when the loading increases, the stiffness is changing. So you don't have 1k, but you have a series of coefficients k. So contact position changes. So if you have general contact, you will have to use nonlinear. We'll talk about a bit more in details about all these points right after. Large deformation is happening, then you use nonlinear too. If you have big displacement, if you have a very high stress levels and it approaches the yield point of the material, or if you have deformation which is gradually increasing due to a long period constant load, all that is nonlinear. So linear analysis, is correspond to a linear equation, but nonlinear analysis has a nonlinear equation. So how to solve a nonlinear equation about for this relation? So the first method, and the method which is used in nonlinear static analysis, is to divide the total force in a curve. So the first method is the one I was just talking about, the incremental method. So first step, second step, third step. So you see the stiffness is approaching the curve. But there's a big problem in this method. The problem is that there's a big error at the end. So actually, how to correct that? Well, there's an improvement to this method, which is called the Newton-Raphson method. So during the Newton-Raphson method, at each load step, an internal stiffness iteration is performed. So the error is reduced, and you can see it fits much more the initial curve. So, okay. Now, for the Newton-Raphson method, you have, as you can see, is what I just told you, the error is decreasing at each step. So this is the first increment, second increment, third increment, so the error is converging and progressively being reduced. So how do we check this error? There's a parameter in the analysis which is called the error tolerance, which is actually the measure of this error. And there's three types of error tolerance that I will just show to you. So the first one is if you measure the displacement. So this is the error in displacement. The second type is the error in loading. And the third type is the walk, so the surface under the curve. So these three types of convergence criteria can be used. So usually only two convergence criteria are combined together to obtain satisfying results. So you can either use displacement plus walk or load plus walk, which is in practice used more than the other one. So a simple example, in this, if you have a curve which is more like that, you will use the load criteria. If you have a curve which is more like that, you have to use the displacement criteria. Okay, now we'll see the procedure and the option in the nonlinear analysis. I hope I'm not going too fast. Okay, let's continue. So this is the basic process in Midas NFX for performing linear analysis. So first step is to prepare the model, to assign the material, to apply the element properties. Then you have to prepare the mesh, to assign the boundary condition, insert the loading, and finally perform the analysis and check your results. So what is the difference with nonlinear? Well, it's almost the same, but there's a bit improvement, let's say, at some of the steps. So the first one is the material assignment. So at this step, you will have to use material nonlinearity assignment. The boundary condition, so use of nonlinear contact, for example. And when you create the analysis case, you have to activate the geometric nonlinearity, and you have also to, let's say, to choose well the nonlinear options, like the number of increments, for example. So how to create a nonlinear analysis case in NFX? Well, it's very simple. It's exactly like doing linear analysis. The only difference is that instead of, when you create your analysis case, instead of choosing linear, you choose nonlinear in the tab. You have also another way. You can go in the panel, in the walkthrough in the left, and right-click and choose nonlinear static, so it will directly create the nonlinear static case. There's something to know. The one important thing is to check the subcase control option. So the first thing, you have to click on the subcase, and the subcase control will appear. Then, in this subcase control, you have to check the option geometry nonlinearity. So if you have this geometric nonlinearity in your model, you always have to check this option. Otherwise, you will have very strange results. So when it is not obvious to consider large deformation, the best way is to check it first, and then you evaluate the deformation results later. And if you see the deformation is not so big, you can uncheck it, and the analysis will be quicker. Now, another parameter which is very, very important is the number of increments you are using. So if you have a model like that, so give you an example for a load of 100 Newton. If you choose 20 increments, the load will be 5 Newton for each step. So you have to think first when you do the analysis, these loads will be small enough to be performed at each step, let's say in a linear way at each step. Then, second thing to check is the convergence criteria. So I just talked just before what it is. So you have to check either load, displacement, or walk. Remember not to use the three criteria at the same time, because it will be too difficult to converge. Or if you use only one convergence criteria, it will be very easy to converge, but your error will be very big. So 2 is good. Now I will talk briefly about the subcases. So there's something which is very useful in nonlinear analysis, is that you can use subcases to perform a sequential movement. So give you an example. So the first example, you want to perform like that, so you want the solid to move. So you can divide that in 2 steps. So the first step will be subcase 1, the subcase 2. Second example, go down, let's say, and go up again. Okay, now before we talk about the geometric nonlinearity, I'd like to show you in NFX how it works to perform the analysis. So for the first tutorial, I will use the designer mode. Designer mode is more simple than analysis mode, and you will see it's quite easy to perform any type of analysis, even nonlinear static. So I will begin by creating a new window, so it's done already. Now I will import a CAD model, so I click on Import CAD, and I choose my model, which is a leaf spring. So this is a model quite simple, composed of a spring and a plate. So the first thing I will do on this model is to create some materials to assign to the spring, because I will use nonlinear material. So I would like to assign this nonlinear material. So we'll click on material, and you see that you have different types of tab here. So the first is for the linear material, so I'll click on nonlinear material, and here I will enter the data for this nonlinear material. So I will call it spring, enter the elastic modulus, the Poisson's ratio, and as I will not use gravity, I don't need to enter the mass density, so I will left it as 0. And now the most important step is to assign the stress and strain data. So for that you have to create the stress strain curve here. So what I will do is I will just take the data from an Excel sheet that I created before. So this is data, so I will copy and paste these data into NFX to create the curve. Now that the curve is created, I click on OK, and don't forget to assign it here in the option. I made very frequently this mistake, so you create the data and you think why it's not working. So don't forget to assign it. Click on OK, and now you generated the first nonlinear material. Now I generate another one, which will be for the plate, so I will call it rigid. It will be linear material, and I will try to import a very high elastic modulus, and I'll just choose the same Poisson's ratio. Now you have to assign that. So if you go in the worktree, you see you have three materials. So the first one is the one which is created by default, the alloy steel. So I will not use it. I will go in the tool and change the material color, so you will see which material is assigned to which model. And I will just take the spring material and drag and drop it on the spring, and do the same for the plate in order to assign the right material to my model. Now let's come back to the geometry color, because I prefer the green and the blue. And now that we've done that, the next step is to create the contact between the two parts. So you can see that there's actually a gap between the two parts at the beginning. So it is not welded contact, it is general contact. So I'll go here in model, click on contact. I will choose general. I will choose I will choose manual contact, general, as a master I choose the surface of the plate, and as a slave surface I choose these two parts of the spring. And I will assign some contact parameters, so I click here and I just call it friction. You can give the name you want. For the coefficient of static friction I will input 0.3 and click on OK. Same, don't forget to assign it, and click on OK. Now you can verify that your contact have been created in the walktree by clicking, and you see on the screen you have the two planes are shown separately, so red is the master surface and the blue one is the slave one. Next thing to do is to assign the boundary condition to this model. So let's click on support, and I will select these two faces here and just pin them. Click on pin, apply. Now I just realized that I didn't told you what I want to do. So actually I want the spring to go down again the plate to deform with plastic deformation, and then I will make it go up again. So I have to fix some translation of the spring, because I will fix the TX and TY translation. Click on apply. And now I have to apply my loading. So my loading will be translational displacement. So I select the same face. I will assign the displacement to this face. I will give a name. So I will call it 8 mm translation. And I just check the Z option and enter -8. So click on apply to generate the first loading. Now I will generate a second loading, which will represent the comeback to the initial position. So Z 0 mm, select the same face, and click on OK. So I will go in the walktree and check that these two static loads have been created. Okay. Okay, now next step is to mesh the model. So for that, very simple, click on Auto Mesh, select the two parts, and select the appropriate size, and click on OK. Okay, now it's done. And let's create the nonlinear static case. So I click on General, Nonlinear Static, and here select the nonlinear static. So you see that you have access here to all the type of analysis you can perform in NFX. So choose nonlinear static. Next thing will be to create a subcase. So to create a subcase, you have a button here. Click on button. Okay. Enter initial position for this subcase. Now I'll change the name of the first subcase. So you have to click to F2 on your keyboard to change the name. And I will call it 8 mm translation. Now click on this button to assign all the loads to all subcase, and I will drag and drop again the load. So the initial position out from the first subcase, and okay, so if you see what it does, the first subcase make 8 mm translation down, and second subcase it come back to the previous. So click on Analysis Control, and here I will set the number of increments. So in this case I will just use 20 increments for each subcase. Convergence criteria, okay, and don't forget to check the geometry nonlinear option. Now click on OK, and it's time to solve. So okay, now the solver will begin to solve. So due to the broadcasting at the same time, it's maybe a bit slower than usually. So when you are performing the analysis, at the same time, you have a graph which show you the maximum displacement in function of the load scale factor. And if you look in this output window, you have several things. First one is the increment, and then you have the iteration. So this is the inner iteration of the Newton-Raphson method I was talking about. Now here in this part you have the checking of the convergence criteria, and as soon as these criteria are verified, you will have the word converge. If it doesn't converge, the solver will automatically cut into your increment and perform in 2 times. So because if it doesn't converge, it means that your load step is too big, your increment is too big, so it will divide it automatically. So the number of iteration, of course, depends on your model. Sometimes it will be quite difficult to reach the right number of iteration because you have a very complex model. So in this case, you have to mesh it more smallly in the area which requires more detail. There's another thing that you can do in NFX 2013 is that you can check the analysis during the computation. So if you open the result file, so the analysis will continue, but at the same time you will be able to check. Also here I think I loaded the wrong results. Okay, so here you have the curve. Okay, it's almost finished, so I'm 65%, 70%. So you see the 2 subcases are subdivided on the screen. So this is the first one and the second one. Okay, now analysis is over and I got the results. So this is first subcase and second subcase. So let's check the first subcase first. So you have basically 3 types of results which are by default. So tensor form is a stress. And using this bar, you can directly see the result of each subcase one after the other. So here you see this spring which is going down and going up again. I will use the deformed feature so you can see the initial shape. So this is the difference between the initial shape and the deformed shape at the end. So maybe it's more interesting to view what is happening for the solid form stress. So you see it go down and go up again, and here you have the plastic strain which are still in the model. Now if you want to view an animation, you can click on animation and you will have animation of your deformation. Okay, let's come back to the presentation. And let's talk about the next subject, which is the geometry nonlinearity. So, well, basically the geometric nonlinearity means the large displacement or the rotation in the structure. It can be also a large strain, and it is basically appearing when you have a load which is too important, and then your model is deforming. Second type of nonlinearity, elastoplasticity. So today I will only talk about elastoplasticity. I will not present hyperelasticity. So in linear analysis, the deformation of material is always considered as elastic, but in nonlinear material, you have plastic deformation, as you just saw during this tutorial. So nonlinear analysis with nonlinear material has been used, and you have several types of curves that can be used. One is elastoplastic model, for example. So loading, plastic deformation, and unloading. So it's exactly what I performed during this analysis. You have different type of nonlinear material, which is called hyperelastic, and it is basically for rubber materials. So this type of curve is actually nonlinear, but it's how to say, it's a type of nonlinear material, but the deformation is always coming back to zero. So it's a kind of nonlinear elasticity. Then you have something called the viscoelasticity, which is the creep models, for example. And in this case, the stress is changing with time. So you have a strain which is caused by the time. This is the curve for elastoplastic model. So I will not do today a course about material, but this is very simple knowledge. So first you have elastic module. So in this area you can perform elastic linear static analysis. Then as soon as you go over the yield stress, you will have perfect plasticity for a small range of deformation. Then you have what is called the deformation hardening and necking and the rupture. So different curves here are caused if you use engineering strain or if you are using the real strain. Now nonlinear contact nonlinearity. So first thing is, what is the reason to use contact? So it's a very, let's say, common knowledge. When you have a load which is applied on the model, of course, it is deforming. And how is it deforming? Because the influence sent to the elements and shared between the nodes, the influence on the nodes is actually shared because of the elements. So the elements are playing the role to propagate the loading. But if the nodes are not connected together with elements, so they cannot transfer the effects of the loads. So in real models, you have more than two bodies, and it's quite difficult to connect the nodes together. So this is why we're using contacts. So if you have no contacts, in this example, for example, the two bodies will simply penetrate one another. So you have no mutual influence between the nodes. If you have a contact, then as soon as your two models enters in contact, there will be a detection of the contact, and it will you will have the contact creation. So what makes this nonlinearity phenomenon? There's several things. The first one is that the contact boundary and the contact stresses cannot be guessed in advance. So there's a constant research of the contact boundary when you are performing the analysis. So the algorithm need at each step to verify if there's a contact or not. Then, if you have rapid change in the contact force, before the body touch each other, the contact force is null and rapidly increases at the moment when the contact occurs. So this is also a cause of nonlinearity. Now, let's talk about the different types of contacts. You have the linear contacts and you have the nonlinear contacts. So, welded contact, sliding contact. You have vertical behavior and horizontal behavior. So for the welded contact, there's no vertical separation and no horizontal separation either. For sliding contact, which is also linear type of contact, you have no vertical behavior, but you have a small sliding which is authorized. As soon as you use nonlinear contact, you have Ross contact and general contact. So the most used is the general contact. It means you can have separation in vertical way, and you can have as well sliding between the parts. So it considers the friction. For the Ross contact, you can have separation as well, but you have no sliding. So linear contact can be applied in nonlinear analysis, but of course nonlinear contact cannot be used in linear analysis. And if the friction is used, what you have to know is that the shear stress will happen before the sliding in the movement direction. Okay, now before talking about the last part, we go to the second demonstration, second tutorial. I will close this model. And for the second model, I will show you the Gearbox example. So we'll go into the analysis mode. So it will be an analysis a bit more complex than the first one. And I hope you can learn a bit some modeling knowledge, because it's very important to model, for example, gears for the engineers. So I'll create first open a new project. So it will be 3D. Okay. Then I will import my CAD model. So it will be step model gear. Okay. Okay. I'll hide the guiders. And the first thing I will do is to create a material. So actually, I will just use linear materials. So I already have alloy steel, so I will just use this one. Now I have to create a property. So I go in the property button, create, 3D property, and I will use the alloy steel. If you want to modify some parameters in your material, it's always possible to edit the material, and you can at any time change the coefficient. For example, if you want to enter the Poisson's ratio, you can modify it like that. Now, next thing I will do is I will create another property, which will be a spring. So you have order here, and create the spring property. So for the spring constant, I will use 500. I will change the name to spring and close that. Now, next step will be to mesh this model. So to mesh it, I will try to do simple, go into the mesh tab, go in 3D, and in this specific case, as your model can be extruded around Z direction, you can use map solid, which will give you much better mesh. And so I select the two objects, enter the right mesh size, so I will use 0.6. You can enter a name here in the mesh set if you want. You can call it gear mesh. Click on OK to generate the mesh. Now I have to create some rigid links in order to make all that rotate. It's not as simple as we can think. So I will go into the top view, go into the element create, and I will create manually some rigid body elements. So go in the other tab, rigid body. Here I will have to select this area around the gear. So I will go in the selection tool and select the circle selection. Now simply select like that and click on apply. So for the first one is okay. Second one, sorry, you have to choose well the middle. Okay, I will try to be a bit closer. So you have to choose a bit the... Okay, now it's good. Otherwise it will not rotate around the right position. And click on OK. Now next thing will be to create a node. So I will use this node to assign the spring. So you see the gear is not exactly at 0, 0, 0 position. So I will go into create a node, enter the value 0, 0, 0, so initial position, click on enter, and you see this node have been created exactly at the initial position. And now I will create the spring. So I will go again and create other, and here in this tab you have to choose a spring. Click on the two nodes to create the spring, and you have to choose well the degree of freedom which is assigned to these two nodes of the spring. So here it will be the rotation around z-axis. Click on OK to generate the spring. So it's actually here in yellow color, so if you want to change that to view a bit more, you can go into these options. Okay, default mesh set. Oh, this is the spring, I'm sorry. To choose the, so you can change the property of the mesh by acting like that in the property window. Okay, now the spring. And now the next step, which is also one of the most important, is the constraints. Because if you don't assign the right constraint, your analysis may not converge, so you'll have a problem of degree of freedom. So in all assembly, the number of degree of freedom you are assigning to the model is very important. So first thing is I will constrain this extremity of the node. So I will click on fix it. I will, sorry, I didn't choose the right element. I want to choose this. This element, this node, sorry. Ah, here, okay. Fix it, okay. And now I have to assign another constraint. So I will go into advanced option, and I will constrain everything except the rotation of in Z direction. So for these two nodes, so the centers of the gears. So verify that it is written two objects. Okay, one. Okay, two objects. Click on OK. And now the next step, which is almost the last one, you have to assign a moment and a displacement. So on one of the gears, I will assign a moment. So here you have function to assign moment. So again, I will go closer and select the object, the node here in the center, and enter a moment in z-axis direction. It will be a moment of 100 Newton millimeter. You can call it, you can give it a name if you want, you can call it torque. Apply. And now on the second gear, I will apply a displacement. So click on displacement, select the central node, and here it will be a rotation of 20 degrees. So actually here the values are in radian. So I have 0.43633, which correspond to 25 degrees. Call it rotation. Click on OK. And last step is the manual contact. So this is very important, because right now I send some loads, some boundary condition, everything, but I still have no contact between the two parts. So to assign that, I will do two things. In the walk tree, I will hide one of the gears and then go to manual contact, so and assign the general contact. So you have several types to choose the master surface, so you can choose either the elements or the faces. So in this case it's more simple to choose the faces, geometric faces. Now just activate again the second gear, and you see you still view the first faces in contact. So now you have to select the contact of the slave faces. 6 contact is contact. Okay, click on OK, and you can go in the contact parameters to view the contact, so to be sure that you assign the contact to the right faces. And now we're ready to create the analysis case. Nonlinear static. Okay, edit this analysis case, and in this case you have to first click to the subcase, and you have the subcase control, which is a pairing. So it's a bit different than in the designer mode, but don't forget to do that because it's very important. You have to check the geometry nonlinearity, enter the number of increments. Now choose the right convergence criteria, click on OK. OK, and you can launch the analysis. So actually in this case the analysis is taking a few minutes, because nonlinear static is not as let's say quick than linear static. So you see I only have 4% and the graph begins to be drawn. So what I will do is I will just stop it and I will load a model that I already done. So you see that if you stop the analysis, it's possible to view the first subcase that already have been computed. So I will open directly a file that I already created before. I'll have to wait a few minutes that it loads all the subcase, all the datas, sorry. Okay. And don't forget to put the result to real deformation, because otherwise you will have something quite strange when you have a movement. And now you can view the gears which are rotating. So this is the displacement, but let's check the solid von Mises stress. And you can obtain quite nicely the stress between the two gears. So actually here the mesh is a bit coarse, so if you want to get better results you will have to mesh it much more than this, but this is just to show you the process of analysis. Okay, now let's come back to the presentation, and I have a little summary about some tips which will be very useful for you if you perform nonlinear static analysis. So the first one is that it's always better to use linear analysis first before performing nonlinear analysis. Why? For several reasons. The first one is that the stresses and first one, if by performing the linear analysis you can judge whether or not to perform nonlinear analysis. So it will depend actually on the deformation. If the stresses or displacement are too large, so in linear analysis, then the design of the product has to be reviewed, and so you have to perform nonlinear analysis. Then another thing is that you can preview, let's say, the areas where the large stresses or deformation happen during the analysis using linear analysis. So it will be faster to use linear to do that, and to have finer results and better accuracy, you can perform nonlinear. Then using linear static, you can also preview the areas where the contacts will happen. So it will be more effective to use first nonlinear linear analysis. Second tips, which is also very useful, the parameter setting. So it's a kind of thing where you think maybe when you begin it's not so important, but you're wrong. It's very important, and the most important parameter is the load increments. So sometimes you do the tutorials, you saw 20, 30 increments, you think it's okay, I will put 20 or 30 increments, but think always in your situation how many increments you need. So sometimes you will need 200 or 300 increments, so you really have to use the right number of increments. Then convergence criteria selection, geometric nonlinear option, or other parameters you can also set. So I didn't talk about that during this presentation because I tried to make it short. You have line search method. Contact parameters also are important, like the stiffness of the contact. Now another thing you can use is the restart function. So I didn't speak about that either, but you can discover it. The restart function can be used to do again an analysis that is not that you have stopped during the process. So if you perform, because I will explain why you have to use that, because nonlinear static are taking a lot of time, and sometimes it's diverging just before the end of the analysis. So at this time, if you have to do everything again, it takes a lot of time. So using restart, you can directly take off from the last step. Then, of course, you have to understand the principle of these nonlinear analysis types, so the geometry, the contact, and the material. This is very important. Now, the tips number 3, which is also useful, is that you always have to begin with the appropriate modeling for nonlinear analysis. So, two things: analysis speed and convergence will increase a lot if you have the appropriate model, because maybe linear static is quite fast. So for big model, you can perform linear, but for nonlinear it will not be so fast. So actually you have to simplify as much as you can your model. So how to simplify it? Several methods. You can use symmetry condition when possible. Use the beams, the shell, or the flat idealized element when possible. So for example, I give you an example, you have a 3D model. 2D will go much faster than 3D. So in this case, you can use the mid-surface option, for example, to create a 2D surface, if it's possible, and perform a nonlinear analysis on it. Then minimize the use of nonlinear material model. So if you don't need to use nonlinear material, just don't use it because it increases the computational time. create dense and smooth mesh in areas of high strain. It's very important to get accurate results. And when possible, use the rotation or extraction feature to create nice mesh, so it can be hexa or peta element meshes. Now, also pay attention to mesh quality, the aspect ratio, the skew angle, and everything, because it can create convergence problem if you have bad mesh quality areas. Okay, now if you want to learn more about NFX, the tutorials, and you want to see, for example, some user interviews, you can always go on my YouTube channel. So you will have some webinars which are registered on it, some tutorials for NFX, some application demo, user case, and a lot of things. Now I'd like to talk briefly about the next webinars we have planned. So the next one will be on the 18th of July, done by Piotr Stepien, which is a Midas NFX CA analyst. And you can sign up on Midas NFX website to attend these webinars. Then on July 19th, I will perform for you a CFD analysis webinar with NFX. So we'll see how to use flow analysis in NFX. And if you are not a Midas user yet, or if you want to try NFX, you can always go on the website and request for the 30 days trial. So go on midasnfx.com. We will receive your email and send you the 30 days trial. So the 30 days trial is provided with full options. So you don't have any limitation in this trial, so you can really test everything, even the CFD. So if you're interested, just try it. Okay, thank you very much for attending this webinar. And right now I will answer to some questions. So if you have some questions, you can leave them in the chat section. So I see that my colleague Apurv is already busy by answering all your questions. So I'll see a few questions. So is it possible to import a DXF file from AutoCAD? Yes, Midas NFX provide DXF import. And also it supports the import of 11 types of CAD models. Is there any way to speed up nonlinear solution Midas NFX from computer hardware point of view? Well, of course, if you have a good computer, it will go faster. So I suggest to use a 64-byte computer. I'm using just a desktop with 16 giga of RAM, and it's going really fast. Actually, it's working well as well on a laptop, but of course it will be faster. And the must, let's say, is to have a small workstation with 8 cores, because as you know, NFX doesn't limit the number of cores that you are using, so you can use 4 cores, 8 cores to compute, and it will be always faster. What if the results are not converged? If the analysis stopped by the program, or is there an option to make the software continue the analysis? Well, yes, it's what I was talking just at the end, which is called the restarts option. So I didn't talk about that during this presentation. If you want to know more about this option, you can send me an email and I will answer you how to use this option. Okay, I think it's almost the end of this webinar. So I would like to thank you very much for hearing and be here for this webinar. I hope you will be able to join also our next webinars that we're organizing. So go in the Midas NFX website and check the list of all the webinars. And we are waiting you to the next session. Okay. Bye.